Hello everyone. Today we will continue our remote sensing image processing class. Today's lesson is radiometric collaboration and atmospheric correction. First, I will introduce myself. My name is Ronghai Hu. I come from College of Resources and Environment, University of Chinese Academy of Science. My email are listed as follows: my name at ucas.ac.cn. If you have any questions, you can reach me by this email, or you can also find me in the WeChat group. The radiometric collaboration and atmospheric correction are very important for quantitative remote sensing. First, we get the raw data, the digital number of the sensor. The raw data from the sensor is only the digital number. It does not have any unit, and it does not have physical meanings. We could identify some object for the image, or we could also do image classifications with the raw data with the digital number. But if we would like to do quantitative analysis, we should convert the digital number to a quantity with physical meanings like radians. The radians describe the radiant flux per unit solid angle and per unit project areas. The procedure to convert the digital number to the radians, this procedure is called the radiometric collaboration. Second, due to the sun's atmosphere evolution and the atmospheric condition, the energy that sensors on aircraft or satellite record can differ from the actual energy emitted or reflected from a surface on the ground. So, in order to obtain the real or true ground radiance or reflectance value, atmospheric correction should be done. Atmospheric correction is to convert the radiance or the top of atmosphere reflectance to the surface reflectance. Radiometric collaboration and atmospheric correction improves the interpretability and the quality of the remote sense data. They are particularly important when comparing multiple data sets over a period of time. The procedure of radiometric collaboration and correction process are listed as follows. First, we get the digital number, the raw data from the sensor. Then, we will convert the digital numbers to radians based on the rescaling factors provided in the metadata file. Then we get the at-sensor radians. Then we will convert the at-sensor radians to the top atmosphere reflectance. Top of the atmosphere reflectance. It requires additional information like Earth-Sun distance, the solar zenith angle, and extra atmospheric irradiance. When we get the top of the atmospheric reflectance, we will still apply the atmospheric correction to get the surface reflectance. Due to the existence of the atmosphere, the top of atmosphere reflectance does not equal to the surface reflectance, so we should do the atmospheric correction. It requires the knowledge of atmospheric condition at the time the image was required. That means if we do not do the atmospheric correction, we know the atmospheric condition it changes with the time. So with the same object at the ground, it means it has the same surface reflectance, but at different atmospheric condition, we will get different top of the atmospheric reflectance. Now we will go to the practice time. In the folder of today's course data, we have 3 files, the PPT and the PDF. Then we open the PDF. The radiometric collaboration, we also could call it radiometric correction, and also the automatic correction. The radiometric correction and atmospheric correction are done to calibrate the picture values and correct for errors in the values. The process improves the interpretability and quality of remote sensed data. Radiometric collaboration and atmospheric correction are particularly important when comparing multiple datasets over a period of time. Because if we want to compare the multiple datasets over a period of time, we should make sure if you have the same object, it should have the same output data. For example, it should have the same surface reflectance. The energy that sensor on an aircraft or satellite is here recorded can differ from the actual energy emitted or reflectance from a surface on the ground because of the existence of the atmospheric conditions. This is due to the sun's azimuth and elevation that influence the energy observed by the sensors. Therefore, in order to obtain the real or true ground radiance or the reflectance values for comparison, the radiometric errors and atmospheric effect should be accounted for. The radiometric calibration and correction process, it consists of 3 steps. The first step is convert the digital number to the at-sensor reflectance. Then we convert the at-sensor radiance to the top of the atmosphere reflectance. Then, also the most complex procedure, we will convert the top of the atmospheric reflectance to the surface reflectance. The first is the radiometric collaboration. This procedure is to convert the digital number to radiance unit. The radiometric collaboration is generally very straightforward and very intuitive. Because the sensor records the intensity of the electromagnetic radiance for each picture as a digital number. For many sensors, these digital numbers can be converted to more meaningful real-world units like radiance, reflectance, or brightness temperature. They are almost the same. The brightness temperature is usually used for thermal remote sensing. Sensor-certified information, specific information is needed to carry out this calibration process. The first or the most widely used parameter is the radiance. Radiance can be converted from the digital number if the image have gains or offset for each band. Usually, the gains and offset for these bands can be found in the image header or metadata files. The equation is very simple. We already know the digit number. The digit number is the data restored in the files, so we already have the digit number of each pictures for each band. And if we have the gain and the offset for this band, we can convert the digit number to the radians. Very simple with this equation. The reflectance, here it is the top of atmosphere, or the TOA reflectance. It ranges from 0 to 1. Top of atmosphere reflectance is available if image have gains, offset, solar irradiance, sun evaluation, and acquisition time defined in the metadata. This equation is a bit more complex, but still very simple, because we already have the air from here. It is the radiance. We just need the additional distance, solar irradiance, and the sun evaluation in degrees. Then we can calculate the TOA reflectance. The brightness temperature is another variable. It is only available for Landsat 8, ETM Plus, and TM thermal image. Brightness temperature in Kelvin are computed as follows. In addition to the air, the radiance, it only needs two parameters, the K1 and K2 calibration constant in Kelvin. The atmosphere correction is much more complex than the radiometric calibration, because we only need some parameters and the equation we could do the radiometric calibration. But for the atmospheric correction, it is more complex because there is a lot of process, including scanting, reflecting, and a very complex procedure in the atmosphere. So generally it will need a very complex model, like some radio transfer model, to produce the surface reflectance. The atmospheric correction is a process of removing the effects of the atmosphere to produce surface reflectance value. Atmospheric correction can significantly improve the interpretability and use of image. Ideally, this process requires knowledge of the atmospheric condition and also properties at the time the image was acquired. Atmospheric models can be used to account for the effects of scanning and observing in the atmosphere. A number of parameters are required to accurately apply atmospheric correction, including properties such as amount of water vapor and the distribution of aerosols. Sometimes this data can be collected by field instruments that measure atmospheric gas and aerosols, but this is often very expensive and time-consuming. Other satellite data can also be used to help estimate the amount and distribution of atmospheric aerosols. Many surface packages include spatial atmospheric correction modules that use atmospheric radiation transfer models to produce an estimate of the true surface reflectance. Then I will show the detailed steps for the radiometric calibration. The following tables list the calibration opinions of ENVI that are available by sensor types. Use file open menu opinions and choose the Me data file listed in the table. We can do the radiometric calibration for different sensors. This is because the calibration parameters are stored at a different place from the Me data file for different sensors. And ENVI put this together. So we just need to choose the corresponding sensors. The ENVI will find the calibration parameters automatically. We can see that what ENVI can do here. It can open a lot of data format like the EO1 Hypering Leaf 1 data project. This is hyperspectral sensors. And Gaofeng 1. Gaofeng 1 is a Chinese sensors with high resolution. And GUI 1. This is also a high resolution sensors. Iconos, a Japanese high resolution sensors. And Landsat Caesars with Landsat TM, Landsat ETM Plus, and Landsat 8OLI TIS data. This may be almost one of the most widely used remote sensing data products. And it also have QuickBird high resolution data, and the Sentinel-2 and Sentinel-3. These are also very widely used new sensor, relative new sensor, and Spot, and also Worldview, and Ziyuan Caesars satellite. They are also Chinese satellites, and they are also the method to open this file with ENVI. So with Landsat ETM, we just need to open the Me data file, and with mtl.txt or the wo.txt or the MET. I think they are used for different sensors. For the TM sensors, we use mtl.txt, and we only have mtl.txt in the folder. ENVI automatically calibrates the following data type. For this sensor, it's calibrate for most sensors, ENVI will output radiance. But for the modest sensors, it also automatically compute emissivity and reflectance data without unit. Modest is a model resolution sensor, maybe the most widely used medium resolution sensors that for global research. And then we will open the ENVI. First, we will open the ENVI. We will open ENVI 5.3 with a new vision. The ENVI software is quite large, so it will take some time to launch the ENVI. And we will also see the data. The data are in the folder. It ends with point .tar, point .gz. It's a compression file. It is an official compressed file. and it is comprised, I think, in the Unix or Linux system. So in Windows system, we will have to unzip it maybe twice. First, we will unzip it to a folder name and with point tar, and we open the folder. So we will find a file and with point tar, and we will uncompress it twice. Then we have a folder. We will have a folder without extension. Open it. Then we can see the data products here. We will have 7 bands, and an overview image. And this point, I think, is a GCP point. And here we have several files. A file and with GCP point txt, I think it's a GCP points data file. And an mtr point txt, this is the most important file, the metadata file. And the var.txt, and also the readme. In the readme, we can get a lot of information we need. With this information, we can also process the data without ENVI software. We can do coding by ourselves if we can understand the organization of the data. We can view it. We do not have to master it, but we can see what this file offers and what there is in the data file. And this is a table of content. First, we can see the introduce of the products, and we can also find more information for different products from the web. And also, this is the description of the format of the different sensors. If we would like to process the data by ourselves by coding without ENVI, I think we will need this information. And also the organization of the file. This is, I think, is somewhat useful. So we can say this is the file naming convention for the Landsat GeoTIFF data. The first letter, L, it is short for Landsat. And the second letter, it is short for mission. E for ETM plus data, T for TM data, and M for MMS data. Here, in our data, it's T, so it is and for TM data. So our data is TM sensor data. The third letter is S. It is short for satellite. It is a number. 7 for Landsat 7 is ETM plus, and 5 for Landsat 5, the TM sensor, and 4 for Landsat 4. Here on your data is 5, so it's a Landsat 5 TM sensor. And the PPP, the three numbers, it is the starting path of the product. In our data, it's 1, 5, 1, 2, 3. And the starting and end row of the products in our data is 0, 7, 2. And also the acquisition years in our data. Our data is acquired in 2007. And the DUI, the drilling date, so it is acquired in the 276th day. I think it's about in the end of autumn. And also have the ground station identifier and 2 digital fishing number. And in the data, it's end of BE. It is short for band 1, band 2, band 3, band 4, band 5, band 6, and band 7. And the MTL, it's leave 1 me data. leave one me data. So the MTL file is a me data file. When we open the Landsat 5 TM sensor data, we should open the MTL file. So it will read some metadata automatically. And that is another data format and the gap mask. And here we can also get some general information and documents for different sensors. And there is also some reference and some contact information. If you would like to find some information, we can find them in these in all these links. Or then, if you still cannot solve it, we can contact them to ask for some help. And this is the end of this file. Then the most important file is the mtl.txt file. We will open it. We can open it with any txt software, like here we use Edit Plus. We will have this data here. Here is some description. The generation time of the file, and some Landsat 5, we know it, and the latitude and longitude of the corners of the products, and file name, and the pictures, line samples of the data. And we also have the maximum and minimum actual length in different bands. And this is the data stored in the file. All the data it is integers from 1 to 255 because it occupies the minimum space. And this one is the most important information. This is radiometric scaling, and all our radiometric calibration, we will need these parameters. We will find for each band, we will have two parameters. One is the radiance multi bands, and another is the radiance add bands. These two parameters correspond to the GANs, and the offset. So the multi-bands is the GANs, and the add bands is the offset. So with these parameters, we could also do the calibration process by ourselves. And ENVI, it also uses this parameter to do the calibration process, but automatically. Then we will start our practice. In the ENVI My menu, we choose File and choose Open, and navigate to the folder that stores the data. Make sure that we open the mtl.txt file. It is necessary that we open the mtl.txt. Only in this way, the ENVI can read the calibration parameters automatically. We'll open it. So we have an image like this. We can find it does not like a real image. It is a red, green, blue band, but it does not. It lists the band organization of the true color image, but this image does not looks like a true color image. This is because we haven't do the radiometric correction. So we should do the radiometric correction. First, we will have a folder here, the radiometric correction folder here. And in this folder, we will find the radiometric collaboration. Double click it. We will have a folder like this. There are two choices, the multi-spectral and the terminal. This is because in the Landsat 5 data, there are 7 bands in total, but 6 bands of it has the same resolution. The terminal bands have another spatial resolution, so it are divided into 2 parts. Here we will open the multi-spectral data and click OK. Now we have the radiometric calibration dialog. Here we have the calibration types, the radiance. Generally we will choose the radiance. And the output interleave. We can choose any of these formats, but it depends on our further processing. We should choose the corresponding setting. And output data file is float by default. The scaling factor is 1 by default. We can see the opinions radian here. The radiance is available if image have gains and offset for each band. We already see them in the mtr.txt, and we read these values from the metadata from the sensor list above. The reflectance is from 0.1 to 1. This is opinion available if the image have gains offset, and it will need additional input like solar irradiance, solar aberration, and correction time. From the output interleave job, select the interleave opinion for the calibrated image. BX2 is a band sequential, and BRL band interleave by line, and BIP band interleave by pictures. From the output file, we can choose where we would like to store our file. Here we can create a new folder named output. We open it, and we rename it as radiance. And click open. And here, and the display results is clicked by default. So after finished our process, the result will be displayed automatically. And click OK. The process is starting, and we will find this one is changed. So we will see a process bar at the bottom right of the software. After the blue part reaches the end, the process is finished. Once the process is completed, the result will be displayed automatically. So now we will wait the process. Generally, it will take some time. Now we have a new image. This image, it has the same band organization as follows. The red, green, blue is band 4, band 2, and band 1. This setting, we will find that this is like a true color image. After the radiometric calibration, we already have a true color image. And we can use the cursor value to see the data. In the cursor value, here we will have the data from the true band. The file it means the number of pictures in the image, the samples and the columns. And the data is the value in each band at this point. And we can find that before the radiometric calibration, the data is integers from 0 to 2055. And after the calibration, we will have a result like this. This is the radiance, and with scaling factors of 1. And also we can see the spectral profile. It's here. We will choose from the menu, we choose display, the profile, and the spectral. Now we will have the spectral profile from different space. Here we will find there is 6 bands, so it has 6 values: 1, 2, 3, 4, 5, 6. And this is how we can do the radiometric collaboration with ENVI. And in addition to this method, we have another method. We can also do collaboration. We can also do radiometric collaboration. This is a low-leaf process. I will show you another method, but you do not have to master it, because with ENVI we can do the radiometric collaboration more conveniently. Here I will show you the second method to do the radiometric collaboration. We know the radiance can be converted from dA with this equation, so we can also do it with the band mass. I think you have already learned how we would use the band mass. Band mass can also be used to do the radiometric collaboration. We will choose. The equation is GAN plus multiply the digital number and plus offset. We know that we can find the calibration result from here. We can know the radiometric scaling parameters here. So we already have the multiple band and add band. For the first band, the radiance multiple bands, or the GAN, is 0.766. So we put it here and multiply band 1 and add the offset. So this is the equation of this equation. This is for the first band. For the second or the third band, they are the same. They are the same method. We will add it to list and plus OK. Then we choose the first band. We choose the first band. We will also choose the output file name. Here we will choose radiance. This result is only the radiance of band 1, so we will name it as B1 and click OK. and we have another reference band. Now we can see the cursor value. We will find that the radius band 1, the value is almost exactly the same as the band 1 of the radius data, radius point DAT, because in the radius point DAT, the band 1 is the third band. Let's see, they are exactly the same. When we choose two different places, they are exactly the same. So with the band match, we have already done the radiometric calibration for the band 1. And then we can also try band 2. The band 2 is use the parameters of band 2 plus B2 and the offset parameter add to list and click OK. Choose band 2 and choose radius B2. OK. Click OK. And now we have band 2. The radius of band 2. We will find the radius of band 2 are exactly as the second band of the radius point DAT. That means with the bandmass tools, we can get the exactly the same radius what ENVI does. But ENVI is still more convenient because ENVI calculates the radius of the several band. Here is 7 band or 6 band automatically once automatically. But for almost we should do the bandmass each band 1 band by 1 band. So it is more convenient. But this method is still useful if you have image data. It is not a format supported by ENVI, so we can do this by the bandmass manually. And in addition, we could also do any other different process with the radiation, the radiometric collaboration. We can also do it for the thermal band. We choose the thermal band, click OK. And here we choose the brightness temperature, and choose brightness temperature, and click OK. This is the brightness temperature of Landsat 5. It's the 6th band. We can also do it by ourselves with this equation and with the parameters here. And for Landsat image, because it only have 2 scaling parameters, so if we choose this, we can also do the radiance or the reflectance. We can also try reflectance. But this reflectance, it is the top of atmospheric reflectance. It takes more time. Now still with the causal value. Now we will find we have a reflectance. The reflectance is range from 0 to 1. We can see the reflectance. It's similar as the visible image is similar as the reflectance, but it has different unit. Then is practice time. So please practice this procedure by yourself. The most important procedure is what I write in the PDF. For the bandmass method, it is not necessary to use. It is not necessary to use. It is not necessary to master it. So you can practice it and have a rest.